Okay, so number one to me is just self-explanatory. So you get out of it what you put in. You know, again, I gave you a couple days to do this. Even if you couldn't do the pictures nice, you should be able to compute mean, median, range, all that stuff. Right? It's not timed. You have the resources to look it up. Yeah. I'm not too concerned with that problem per se. Okay, what I am concerned with are these other ones. So problem two. And for those of you who understand this, this is good, but I would also hope you still consider paying attention and doing this slowly, because I don't know if you've noticed it, but we spent an awful lot of time on some of these examples, and that's by design. Again, so many of these things we're doing are just basic fundamental examples or basic models of real world. Again, every time you say, oh, another coin flip problem, don't think a coin flip. Think success, failure, not heads or tails. Think lives, dies, not heads or tails. Think makes money, loses money, not heads or tails. These are simplified models of things we want in the real world. I say flip a coin 4 times. I might think of that as patient takes medicine 4 times, or patient 1 takes medicine, patient 2 takes medicine, patient 3 takes the same medicine, patient 4. Does it work? Does it not work? Do you understand what I'm saying? So even if you think these are silly, they don't have to be sort of always thought of as silly. Okay, so anyhow, we flip a coin 4 times and we record heads or tails. What is the sample space? Now notice I use the word describe. So I wasn't, if you wrote them all out, that's fine. There's 16 of them, 16 elements. You don't have to write them all out. So maybe I'll, you know, I wasn't expecting you to, that's why I used the word describe. So the sample space has 16 elements, and I'll list a few of them. So what is the first one? You might think of it as, we'll use fancy math notation. The first one might be heads, 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 heads. The second one might be heads, 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 tails, right? And this goes on. And then maybe the pattern is we go all the way to the very last one, which is 4 tails in a row. You could write them out. You don't have to. Now, one thing I will say, if you write them all out, it might give you a different perspective on how you do the parts to the problem. Whether you use the sort of shortcuts we talked about with like these axioms of probability, these rules, or you just count, right? Because if a sample space only has 16 elements, most problems I can ask you about it, or most questions, could actually be done by counting. So, for example, what are the number of outcomes where there are at least 2 heads? The easiest way to figure this out would be to do what? The easiest way would be to list them all out and count them. Is there another quick or more sophisticated way of doing it? The answer is yes, but how do you want to attack it? You know, there's lots of symmetries. For example, getting at least 2 heads is the same as what? Well, you can think of it in terms of tails. Do you understand what I mean by symmetry? Since there's only 2 options, heads or tails, we can take advantage of these symmetries if we want cute ways of counting them. So let me sort of write this out. So for B, part 2, I guess, or whatever. Whoa, that ain't good. So one way to answer this is write out all 16. Now, what you might find is you don't need to write them all out. If you start to recognize there's a pattern, then you could say, oh, I see where the symmetry is going to help me handle this. So, for example, here's what I mean. I know there's 16. Oh, my God. No, get out of here. Making all computer all loud. Pardon me, we can't have that kind of malfunction. Hurt my ears. Is that as loud? Probably not for you, but. All right, so here, look how I'm going to write them out. I'm going to write them out in the following sort of manner. I have a heads, 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 heads. So the first row, I'm going to write out all the scenarios where I get a heads first. Does that make sense? And so then I might have a heads, 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 tail. Then I might have a heads, heads, tails, heads. What's that? Oh my Lord. Did it switch like that or did I do that? Sorry about that. My apologies. So the first row is, okay, I'm trying to figure out, is there a cute way that I can write them out where I can sort of make sense of this? What other scenario do I get a head first? Well, I can have a head, tail, head, head. Is there any other scenario where I have a head first? Well, yeah, I can have this. I can have the scenario where I have, okay, what if I have heads and then tails? And then heads, tails. Or what if I have heads, tails, tails, heads? So let me stop for a second and again, I'm not saying this is the best way to solve the problem. What I'm trying to do here is illustrate a very basic way of solving it that only requires you understand what a sample space is and what an event is. It doesn't require you know fancy counting tricks. It doesn't require you know anything about the axioms. It just, all this does is it requires that you can reason what's possible if I flip a coin. So what I want to do right now is I want to list all the scenarios I can think of that starts with a head. And so what I'm going to do is I'm going to first, my top row is the scenarios where I have a head and then I have one tail. Does that make sense? That's just the way I'm thinking of it. Maybe you have a better pattern or one that you like. And then my second row is going to be where I start with a head, but instead of having only one tail, I have, say, two tails. And so there's another scenario where I have, yeah, so now I can go head, head, tail, tail. Are there any other scenarios where I have two tails where I start with a head? And the answer is no. There's none. And so then the last scenario would then be the chance I get a head, and then I follow that with three tails, right? Now, why would I do it this way? Well, one reason I might start this way is because problem 2, part 2 says, or part B says, what are the scenarios there's at least two heads? So in my mind, I said, okay, let me just start writing out where heads happens first. Now, right now I've written 8 scenarios down. These are 8 outcomes. This is half of my sample space. I have exhausted all options that start with a head first. So the nice thing I can do then is now, because of symmetry, I can easily write down the other ones. What are the other options? Well, let's just use symmetry. Instead of all heads, let's say I have all tails. Or I have tails, tails, heads, or 3 tails and a heads, or I have tails, tails, heads, tails. Or I have tails, heads, tails, tails. Or I have tails, heads, tails, heads. Or tails, heads, heads, tails. Now, I should be going a little slower just to make sure that I don't do anything incorrect here. Do I have duplicates? Am I counting something twice when I shouldn't be? Okay, does anybody have a question about this? So now what I'd like to do is I'd like to circle all of them that have at least 2 heads. So this guy has 2 heads. 2 heads, at least, at least, at least, at least, at least, at least. And then down here, I have at least, at least, at least, and at least. That's if I did the problem correctly, right? So how many are there total? Looks to me like there are 11. 11 of the 16. So 11 out of 16 have at least 2 heads. So by writing all this out and counting this old-fashioned follow your nose way, what I can determine is I can answer the third part right now, because now I know the probability of at least 2 heads, I think. And so if I want to do part C, the probability of at least 2 heads would be 11 out of 16. Now, if I want, I can write that in terms of percentages. So that's going to be what? Roughly like 68.7%. So this method of getting this is solely by counting. Now, that's not the only way to answer this question. Alternatively, I could have used sort of what we call our axioms or our rules. So alternatively, the probability of at least 2 heads equals 1 minus the probability. Well, what's the complementary event? If I don't have at least 2, that means I have 0 or 1, right? And so that would be 1 minus, what's the probability that you have 0? Well, that's 1 out of 16. And then what's the probability? You know, if we use our probability rules, this would be that case. Now, how many ways can I have 1 head? Now, the benefit to using this second strategy in blue is I don't actually have to write anything out. I can deduce these numbers right away. How do I get 1/16? Well, one way to think about that is I could write them all out and notice that there's 1. But a more sort of efficient way of doing it is notice that the first toss, what's the probability of a head? 1/2. Probability of a tail is 1/2. So I would have to get what? 4 in a row. So what's 1/2 to the 4th power? 1/16. Now, what's the probability of getting 1 head? Well, one way is to go through this list and count. How many times do I see 1 head? I see 1 head here. I see 1 head here, 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 right? But another way to do this is to think about it as steps, think in terms of the tree. First toss, yes or no, heads or tails? Well, still going to be what? It's going to be 1/2. And then what's the next 3 going to be? 1/2, 1/2, 1/2. So you still get 1/4, or excuse me, 1/2 to the power 4. But how many options are there? Well, for exactly one head, there's 4 options. It can come first, it can come second, it can come third or fourth. So there's 4 options. So you can reason it that way. And this is also foreshadowing what we're going to get into soon enough, which is called this thing called the binomial distribution. We're reasoning successes and failures, or heads and tails, in terms of the rules of probability. And so this would be 4 over 16. So what does this simplify to? This is 1 minus 5/16, which is the same as 16 over 16 minus 5/16, which once again is 11/16. So there is one way to recognize the probability or compute the probability without having to draw anything. Now, I'm not suggesting you would have thought of it this way. In fact, I didn't even want you to think of it this way. I wanted you to write it all out. That's why I said describe it. But now what I'd like you to do is make a connection between the picture and these rules that I'm using down here. That's hard for you to do because you don't understand the rules of probability the way I do. You don't understand the axioms. You're probably not sure why I'm adding these 2 things together. But the rules of probability say that the event of 0 heads and the event of exactly 1 can't happen at the same time, right? And so that means in order to add the probability that one or the other happens, you compute the probability of each and add them up. That's one of the rules that we deduced. We called those, what kind of events were they? Mutually exclusive. It's impossible to get no heads at the same time you get exactly 1 head, right? Does anybody have a question about this? So the purpose of this problem was to see who understood these basic ideas of sample space, but also that once you understand these basic ideas, we can start transitioning into how to use these probability rules, these theorems that we deduce from these axioms, how to use them to make efficient computations. Because what if instead I said we're going to flip a coin 13 times? Then your sample space is massive. So you need to have a more efficient strategy. Okay, so this is the easy, sort of straightforward way in black, and then in blue, it's this very sort of sophisticated way of using these probability theorems, these rules. Anyhow, what about part D, where the probability of no tails? Well, no tails equals, well, what should it be? Well, we can think of it in terms of heads or tails. It's 1/2 times 1/2 times 1/2 times 1/2, or 1/16. However, if you go look at your table, you'll know the only one of them has no tails, 1 out of the 16. So this is 1 out of 16, and the key observation I would tell you to think about is not just think about it as 1/16, think about it as 1/2 to the 4th power. The 1/2 to the 4th power tells us to think of it in terms of an abstract thing. We're flipping a coin, and it can either be 1/2 time its heads, the other half its tails. And we're going to do that 4 times. Writing it as 1/16, you can think of it as 1 out of the 16 total guys in your list. Am I making this clear? I don't know. I mean, I really would, if you want to learn this, I think it's important that you make the connection between the abstraction of these probability rules and the simpleness that you can list out 16 things. You got to make the connection. Okay. And then lastly, for part E, the probability of exactly 2 tails. Well, there's one way we can do it. we could go back to our thing and say, okay, how many of these exactly have two tails? 1, 2, 3, 4, 5, 6. It looks to be 6, I think, right? Let me double check. 2 tails, 2, 3, yep. Right. Okay, so exactly 2 tails. So we think that that's 6 out of 16. Or reason how the experiment can go. How is it that you can only get 2 tails? Well, how many possible ways that it can happen? You can get 2 tails right away, then heads, heads. You can get 2 tail, or you get a tail, heads, tail, head. Or you can get a tail, how did I say that? Heads, heads, tails. So how can you reason, how many possible ways can that happen? And each one of those ways is going to have the same exact probability, and we know that we can add them all up. So if you think about that, what I'm saying by that is the probability of exactly 2 tails is equal to the probability of tails, tails, heads, heads, plus the probability of tails, heads, heads, tails, plus the probability of, say, tails, heads, tails, heads, plus the probability, and that's exhausted all the things that I get at tails first. So now let's say I get a heads first, and I can have tails, tails, heads, plus the probability of heads, and then tail, heads, tail. And then what's the other and final option? The probability that I get tails, tails, heads. Oh, no, I wrote that one already. So what would this be? This would be a heads, and then a heads, and then a tail, tail. And either way, if you think about this, which one is each of these? What's the probability of all 6 of these? Each one of them is 1/2 to the 4th. So the way I would encourage you to think about this, remember, maybe this is me thinking in terms of a mathematician, whereas maybe you're not. One of the things we would like to do if we can recognize things is recognize patterns. And so the pattern I'm recognizing is that if I compute the probability this way, I literally just counted how many there were in a list of 16. And there's nothing wrong with that. It's just if my list had 316 things, it'd be really hard to count. Down here, what's happening at the very last line is I am reasoning how many different ways are there. And we're going to find that there's a pattern for this. There is a pattern for how I got these things down here. And the thing that I'd really want you to sort of ponder is that each one of these guys, this number is equal to 1/2 to the 4th, which of course is 1/16. This guy's 1/16. This guy's 1/16. These guys are all 1/16. So what you really have down here is you have 6 copies of 1/16. Or 1/16 plus 1/16 6 times. And so the probability of exactly 2, what is it, tails I said? 2 tails is 1/16 plus 1/16 plus 1/16 plus 1/16 plus 1/16 plus 1/16. And I'm not writing this out to be ridiculous, but I want you to think about it like this. This is really 6 times 1/2 to the power 4. There's a pattern hiding here. We just have to discover it. And once we can discover this pattern, then we can take the pattern we discovered for this example and we can generalize it to rolling dice where there's 6 options instead of 2. Or maybe rolling 2 dice where there's even more option. So let me reiterate the point of this again. And please, if you have a question, ask. Comments? So there's the hidden thing here is we're asking ourselves, if we have two symbols, H and T, how many different ways can we arrange them? That's what we're asking here. And some of you may have some experience with these counting things. We're looking for patterns to help us count. And there's these things we're going to start talking about called permutations and combinations that give us shortcuts for counting. So the purpose of me giving you this problem on the exam is twofold. One, if you just do the basic stuff we taught you before and did examples, you can answer the question. But you can also view this example from a different perspective, and it can help show us that there's a pattern hiding. And then we can take that pattern that we recognize and learn how to apply it to more complicated things. That's the point. So hopefully you'll give that some thought. I don't know if you will. I'll pretend you do. I'll pretend you. I'll be like, I'll go home, man. I'll tell all the stuffed animals. That's what we do. We practice the lectures with the stuffed animals. Me and the kids, the crumb snatchers, everybody gets up in the room. And I'll say, you guys won't believe how awesome it went today. They are so excited. They ran home and started looking for patterns. And then I realized they didn't. All right, so let's move on then, and we're gonna talk more about these patterns coming up, but I'm trying to stir your imagination, if you will. They are crumb snatchers. What the hell? Just the best thing to describe them as crumb snatchers. They literally snatch crumbs and leave crumbs. They don't care. Lydia, this is what this numbskull yesterday had a plate of fruit. Okay, and she drops it all over the carpet. Now, people in my house are watching the football game. There's people walking all over this carpet. You know what carpets are. There's little fuzz and stuff all over. It's a carpet. She has all this watermelon and all this cantaloupe and all these honeydews, and they're all over the floor, and she's crying because I told her to throw them away. I said, you can't eat this. She goes, why not? Now I'm going to have to buy her a damn microscope and show her why not. I mean, these kids will eat anything. You having fur balls like a cat. Crumb snatchers. Is that not an apt name? It's very good. Crumb snatchers. I love it. It was, well, I shouldn't say that out loud. Anyhow, let's move on to the next problem. Problem 3. Once again, we have a card game now. So we're going to select cards. We're not going to put them back. We want to know some probabilities. Now, we did this one. So what's the probability that you get 3 black cards? Well, this is going to be, you select the first card. How many black cards are there? Well, there's 20. Half of the deck is a black card. The other half's red. So you could think of this as 26 over 52. And then if there's a black one gone, then there's 25 left, and there's only 51 cards now, and then 24 over 50. And so one of the things that we'd like you to notice here as well is that there's a pattern. This one, albeit it might look like a simple pattern, but in the general patterns, not as easy to see, but there is definitely a pattern here that would give us insight to how we might solve this problem in another way. So what I would say for the time being, since it's not, some of you are still not sure exactly how I'm getting these things, what is this number? Well, this number, if I did it correctly, which I think I did, is approximately 0.1176, which of course is approximately 11.76%. So what we're using here is we're using this idea of conditional probability we talked about. Why is the first one 26 over 52? Because half the cards are red, the other half are black. There's 52 total cards, half of 52 is 26. Now, why is the second one 25 over 51? Well, if I didn't replace the cards, I have one less card total. And it happened to be black because I'm assuming I got a black one the first time. So that's why it's 25 over 51. And then similarly, the same reasoning gives me 24 over 50. So again, these probabilities at the second and third step are conditioned. They are a specific, the denominator changes and the numerator changes because they are assuming that we knew what happened at the first step and the second step. Now, the next problem is very similar to this, the next part I should say. The probability of all hearts. Well, how many hearts are there? There's 13. There's 13 of each suit, so 13 over 52. Then the next time, if the first one's a heart, there's one less heart, and there's still one less card in the deck, and so you can reason this guy. So 13, 12, 11. And as you would expect, this one's even less likely than the previous scenario. 0, 1, 2, 9. And of course, this is approximately 1.29%. So these first two are fairly straightforward. And the next one is, it's straightforward only if you use the rules of the probability. So at least one queen, well, that could be tricky. How many different ways can I get a queen? Or at least one of them. So now I have to, how do I want to reason this problem? I could think about all the ways I can get one queen, all the ways I can get two queens, all the ways I can get three queens. That would answer it, but that seems like a lot of work. Or I can ask myself and use the rules, and perhaps that might be the way to go here. I might say, okay, the probability of at least one queen, you might think this is 1 minus the probability of no queens. Now, what's the probability of no queens? Well, that means we can't get a queen on the first time. So if there's 13 queens, then that means what's the probability I don't get a queen? Yeah, so there's what, 39 non-queens in the deck. And then the second time, it would have to be 38 over 51. And then 37 over 50. That would be how I computed this. So before we go anywhere, let's make sure that this is correct. What's 39 and 13? 39 and 13 is indeed 52. So that we at least are checking our numbers. So again, you might say, okay, well, why are you multiplying three numbers together? Well, that is our definition of conditional probability. The first card, this first fraction represents the first card. The first card, if I don't want a queen, there's 39 non-queens. So I have a 39 out of 52 chance of getting a non-queen. Now, assuming I get a queen on the first try, there's 38 out of a total 51, and 38 of them are queens. So that's how I'm reasoning this. Okay, so then I just have to do the arithmetic. And if I do that, Actually, I guess I should use a calculator so I don't do that in my head. I'm losing my mind. I get the following. And by the way, one thing you should do, and it's going to be different for each one of you, depending on how much experience you have with any of these sort of games to begin with. Does the answer seem realistic? So if I compute this number, I end up getting approximately 0.586, which is approximately 58.6%. Does that seem reasonable? Do you feel that you're more likely than not to get at least one queen? Think it's wrong, Anthony? It's good to ask yourself this. I mean, let's trace back to the top. 3 black cards, we got 11% chance roughly. Does that seem reasonable? Well, yeah, it does, because you figure there's a 50-50 chance. That would be like getting, you know, if you put it in terms of like heads and tails, that'd be like getting 3 heads in a row or 3 tails in a row. Only it's slightly different because the second time it's not going to be equal 50-50 anymore, right? The third one. But nonetheless, and in the probability of getting 3 hearts, we would imagine it's going to be less than 3 black cards because there's less hearts. So it seems realistic. But then we come to this one, at least 1 queen. So if I draw 3 cards, should I expect at least one of them? Well, there's lots of options here. The options are I get 1 queen, so here's a good example of when you need to get your intuition in line. Your intuition's telling you something, and it's still, no one's once said what the problem is, or did someone finally actually chat? About time someone chatted out. Yeah, very good. So this number seems extremely high to me. My intuition tells me that if I pick 3 cards, one of them's a queen, that seems really strange. It would be almost 60%. And so what I do is I check my math again, and I realize I made a very, very crucial error. The math I just did here says that there are 13 queens in the deck. There ain't 13 queens in the deck. How many queens are in the deck? 4, right? And so instead of 39, that's what happens when I listen to you students. You say 39, I'm just kidding. But no, so this is a good mistake. Because what we're doing is we're learning. We realize that the answer doesn't match our intuition. Now, that doesn't mean that we did it wrong, but in this case, it turns out we did it wrong. So what do I mean by that? Well, these numbers up here should not be 39, should not be 38, should not be 37. What they should be is how many queens are in the deck? There are 4, which means there are 48 non-queens. And then if I don't pick a queen the first time, there are 47 non-queens out of 51 left. And then the third time, if I don't get a queen, there are 46 out of possible 50 cards that are not queens. That's all right. You'd be surprised how many people made that error on the test, believe it or not. And that's okay. That's why we have these learning moments. That's what we're here for. So anyhow, now if I go to my calculator and do this, excuse me, we get a much more realistic answer of about 22%. So if I go to the calculator and I plug this in, I get this is equal to approximately 0.217 or 21.7%. Now, does that seem more likely? Seems more reasonable than 60%, right? Does anybody have a question or a comment about this? Comments, concerns? Going once, going twice. All right. So let's assume that no one has any beef with this one. All right, next part. At least one club. Well, that's going to be a very similar argument to the one we just did. So the probability of at least one club is 1 minus the probability of no clubs, which would be 1 minus, okay, no clubs. So on the first one, there's 52 options. 13 of them are clubs. So now, how many are non-clubs? 39. So 39 over 52, then if we got a club the first time, the next time there's 38 over 51. And then the last time there's 37 over 50. And this is the number we calculated earlier to be approximately 0.586 or 58.6%. Now this seems more likely because, at least in our minds, we think there's more clubs than there are queens. Another way to think about this from a very sort of raw, your first club, you have like a what? A 1 in 4 chance. The next time you have a 1 in 4 chance. The next time you roughly have a 1 in 4 chance, right? So does that maybe make it a little more intuitive? That's not an actual calculation, but at least you're reasoning that way. Now, again, another way to answer these parts would be to think about how many different ways can you get one club and then add all those up. And there's actually a shortcut to that, which we'll get to soon enough. But right now, let's just try to think of this one way at a time. The purpose of the last part of this problem is to help elude you to that shortcut, right? All right. Does anybody have any questions? Okay, so the way I would have you think, and by the way, when I design these problems, for example, problem 2 and 3 are very similar, but problem 3 part 5 is a much more difficult problem to answer than the other ones. And you know, sometimes when we make exams, we don't always expect that you're all going to get them right. Of course, you're going to say, well, that's mean. Well, no, we're trying to also get you to think about new ideas and to also sort of not just find new ideas, but think of things from a different perspective, you know. And so here's how I would encourage you to think about the last part. So the probability that I get 2 queens and 1 heart. Now the subtlety here is it's possible that one of your queens is a heart. And I didn't say anything about an order. I'm not saying that you have to get a queen, queen, and a heart. you might get a queen, heart, queen. Or you might get queen and then queen of hearts and then something else. So we need to think about all these scenarios. So this one is challenging because one of the queens could be a queen of hearts. So again, I'm not saying that this is the only way to do the problem, but one strategy would be the following. So one strategy would be to look at all possible outcomes for this event. So for example, you might have queen, queen, heart. You might have queen, heart, queen. And then you might have heart, queen, queen. But in these three scenarios, so in these three scenarios, what I might assume is I'm going to assume that that heart is non-queen. So here, the heart is not the queen of hearts. And so you'd have to look at the probability of each one of those things. Then repeat so consider the same pattern when the heart is the queen of hearts. And so then there comes a little nuance here. Did O'Grady mean that you get exactly two queens and one heart? Because if that's the case, and that's how you want to interpret it, which is in fact the way I did mean it, is then you would have this pattern, but it would be slightly different because, okay, you would have queen of, I'll write it like this, a heart, and then a queen, and then no. And then you would have queen, queen of hearts, and then not a queen or a heart. And then you would have the scenario where the next scenario, so you'd have queen of hearts, not, and then queen, and then you'd have the symmetric sort of, I don't know if my notation is helpful or not. What I'm trying to sort of do is say, okay, think of these symbols as the first draw. So if I come up, let me try to make sense of this. And by the way, I'm thinking out loud of this, like I'm trying to show you how maybe I would be thinking about this if I had to do it. Notice I'm not just plugging things into a formula. I'm trying to reason what's happening. So the way I'm thinking about this is my first card is a queen. My second is a queen. My third is a heart, but it's not a queen of hearts. Here I have a similar scenario, it's just ordered different. And then once I realize, okay, down here when O'Grady writes QH, this means I get a queen, but it happens to also be a heart. Then the next card is a queen. It can't be a queen of hearts. It's just one of the other 3 queens. And then here it could be anything, as long as it's not a queen or a heart. So I'm using N for no. This is just, and then I have all these options because I could get the queen of hearts first, or I can get it second. And then in all these scenarios, I can get the queen of hearts first or second. That's the point I'm saying. Now, the next thing is, once I realize that this is the only patterns that matter, the question is, can I actually compute the probability of one of these scenarios? So, for example, up here, what would the probability be? Well, getting a queen right away would be, okay, there's 4, so it'd be 4 52s. Then getting a queen again, there's only 3 left, so it'd be what? 3 out of 51. And then what would be a heart? Well, we're assuming that there's still 13 hearts left, so it would be 13 over 50. Now, these 3 things, there's going to be 3 of these. And then can we compute the probabilities down here? And then at the end of the day, if we can compute all these probabilities, we add them up, and that gives us the probability we're looking for. Now, why do we add them up? Because they're all mutually exclusive. You know, this thing and this thing aren't the same, right? They can't happen at the same time. None of these guys down here can, and none of these can happen at the same time. So one of the rules that we have from our axioms is that the probability of an event is equal to the probability of all the outcomes that are in that event, if you add them up. So all 3 of these, if I wanted to, this is, as we just said, all 3 of these have the probability of, so yeah, they're not the same, right? I mean, necessarily, you have to be careful. So the probability of this creature would be 13. Well, let's just look at them. It can't hurt to keep going through. So the probability of queen, heart is 13 over 52 times 12 over 51 times 4 over 50. And then what would the probability of queen, heart, queen be? Well, that would be 13 over 52 times the heart would be 4 over 51. And then the queen would be 12 over 50. But you see these are just the same things. They're just ordered. Yeah. Why do I have them reversed? What do you mean by that? Yeah. Very good. That would be bad, would it not? So say what you mean what you say. The queen, there's 4 queens. So there's 4 over 52, 3 over 51, and then 13 over 50. We good now? Well, yeah, right. But we good on the top one. All right. See, we're paying attention now. This is always good. All right. The key observation, though, is to see what happens here. So now queen, this would be 4, but then this would be 13, and then this, of course, would be 3. But the point I'm trying to make is these are all the same number, right? Just it's ordered differently. Because the last one is heart, queen, which of course is going to be the same thing. So heart, 13 over 52, and then 4 over 51 times 3 over 50. So if you want, for short, you can say you have 3 of this number, however you want to write it. You know, keep it in order. You have 13 times 4 times 3 over 52 times 51 times 50. So there's 3 of these scenarios. Now, what about down here? Is there going to be some quick pattern here? Because now we have a queen of hearts. Now, this is a little more complicated to deduce. So how many queen of hearts are there? There's 1 queen of hearts, right? And then that means how many hearts or queens are left? Excuse me, there's 1 less queen left, and then there's also going to be 1 less total card. So for example, if I use sort of this Now, if I say, okay, let's imagine I get a queen of hearts, then I get a queen, and then I get neither. Well, this is the queen of hearts. There's 52 of them. Then how many queens are left? Well, we already used one of the queens, so there's 3 out of 51. And then how many cards total are left? Well, if we got rid of our queen of heart, right? So there's 51 cards when I get rid of my queen of hearts. But there's also 1 less heart and there's 1 less queen. So there's 3 queens. So this is where the subtlety is. How many chances are of nothing? Well, I got 2 queens are gone already. One heart is gone. Well, I mean, it's just counting, right? We're only counting, but let's, you got to go slow at this because as we saw, you can make mistakes real quick. So we have this conditional probability. We get a queen of hearts first. That means that there are 3 hearts left. Excuse me, 3 queens for me to get on my next pull. Okay, well, why 48?
Because we're taking all the queens out of it.
Okay, but aren't we supposed to also take all the hearts out of it? We're not supposed to get a queen or a heart. So I think we're in agreement that the bottom is definitely, the denominator should be 50. There's 50 cards. But how many of the 50 cards left are neither a queen nor a heart? So if we already got rid of, if we got rid of our heart, let's start with the hearts. There's 13 of them, right? We already got rid of one of them. So that means that out of those 13, that's 39. But then we also can't choose a heart. Or excuse me, a queen. Can't choose a queen, so there's how many queens are left? There's not 4 because we already got 2 of them. No, there's 2 left. We got 2 of them, right? So that means that there's 39 and then 2 other cards we can't grab. So does that mean let's be careful, is it 37 then? Are there 37 cards left that we can grab that are neither queens? So let's just reverse that. If I have 37 we got to make sure it adds up is what I'm saying. Say I take those 37 cards that are not queens or hearts and I put the 2 queens back in. Then I would have 39 cards, right? And then if I take what hearts am I, or excuse me, the hearts now, if I add those back in, how many are left? See, this is not as easy as you would think it is. And it's not really, mind-boggling difficult, but look how easy it is to get confused. I wonder how many of you, if any, actually took out a deck of cards when you're doing this to think about it. Because the best way to do this part would to literally do that, to take a deck of cards and count. So we're almost out of time, and I don't want to rush this because I think it's important. So I'm going to leave at this point right now. And what I'd like you to really do is, and we're going to do more of this on Wednesday, but I would really encourage you to think about this problem. And even ask, are we even doing it right way? Is there a better way of doing it? I think this is an interesting problem. You might not, but I do. What's that? I know. Oh, you never know what happens. Yeah. Heck, last week it was crazy. We were trying to do our Zoom review for calculus, and it kept kicking us out. It was terrible. I wanted to write a letter to Zoom. All right, but listen, we will, since we're out of time, we will finish this this problem on Wednesday. So ponder it. Think if you ask yourself if we're doing it right, if there's a better way. And I will see you guys Wednesday. Thank you very much. I had fun. I like classes like this. Problem solving is a team. It's the only way. The only way.